It is 7:30. It's a bad deal. Welcome to the Four Lakes Amateur Radio Club meeting for September, and particular welcome to guests since we're doing a collaboration meeting tonight. I'm Thomas, Whiskey November 1 Charlie, Vice President, filling in for our president who is traveling. I'll go ahead and introduce our board members and then just do a quick round to say who you are and why you're here.
Nicholas Lager, KB9 SKW for Secretary.
And board member, KD9 ZUE.
Sam, KI5 POE Treasurer.
Send it back on this side and come back on this side.
Jeff, KE9 CQP.
I'm Doug, W5 WTX.
I'm Tom, W9 TDP member.
Rex, N9 TRX.
Eric, N9 DMF, my first meeting.
Awesome.
I'm John Rummel, member of MAS, the Astronomical Society, and I do not have a call.
It's okay.
I'm Paul, AC9 HF.
I'm Will, W89 MCV, and also a member of MAS. I'm Ben, Kilo Echo 9. Delta Yankee.
So you got it.
Yeah, I did.
Good job.
Yeah, working on that call sign a little bit.
My name's Alex, KC0YHP, I'm a member of Mass National. Andy, AC9CB.
All right. Do a quick round online. Other Thomas.
Evan Thomas, KE9 DFF.
Good evening. Good evening, Thomas, AC9BJ, member.
All right. Mike. All right. Well, we've got Mike there. Kevin does not have a mic tonight. Bob, would you like to say anything?
K5MI said here. Bob Ribbon.
All right. And Greg.
9 AOA, joined back in June.
All right. And Paulette.
Name is Paulette Quick, WB9 VHF.
And our speaker, Dennis.
Good evening, Dennis. Out here in California, W6DQ, and off camera in the wings here is my wife, KF6QNG. That's Lisa, and it's a pleasure to be here this evening with you all.
Very good, thank you. That concludes quick introductions and guests. Was there any commentary on the July membership meeting minutes from our last in-person meeting? All right, as a motion to approve the posted July meeting minutes.
So move.
Okay.
Tom, W9 TDP.
Second.
Second. Doug, W5 WTX.
All right, all in favor of approving, say aye.
Aye.
Any opposed? All right. The treasurer's report. Sam, will you please present?
Treasurer's report. At this time, we have had $1,588 in dues paid. We have gained a new member since the last meeting. We now have 70 paid members. In the bank, we have $3,750.91. We have the CD of $2,066.94 and one of $2,014.96. We had a expense for Zoom of $168.70. And that's it for the
expense. 168. What was the expense? 168.
168.70.
What was the total for the CDs?
So total for CDs is
4,000.
Can I give that to you?
Yeah. You just want to put the total in. We don't need two separate ones listed.
Yeah, yeah, so there's two separate ones, okay. And that's it.
All right, do we have a motion to approve the treasurer's report?
Second,
Sam from the internet.
All right, well, we'll do Tom for the motion and Sam from the internet for the second. As moved, all in favor, say aye.
Hey,
Aye.
All right. That's on the treasurer's report. Then we'll go on to potentially a long section. We're looking for bragging rights upgrades, call sign changes, and silent keys. Does anyone have anything to contribute?
One.
Start off.
Extra as of last month.
Congratulations.
I have a brag.
Go
I
ahead,
placed
Thomas.
in the Missouri QSO party for 2025. I placed second place for Wisconsin.
Congrats.
Other entries for this category. We'll get to my entry in this category.
You need new operators with a new license. Ben, introduce yourself. Come on.
Ben, I,
What's the call sign again?
Kilo, Echo 9, Delta, Yankee, Quebec.
I guess I'm new too. Rex, November 9 Tango Romeo X-ray,
All right.
Hold on, say again.
M9 TRX. Which Thomas may remember came through as a vanity call sign at exactly the same time I was taking my general.
Which confused the paperwork. All right, Thomas, WN1C. I participated in the September VHF contest with a raw score of 630, a new personal best. And with any luck, a top for my very small category in Wisconsin and or the region.
Okay, what kind of test was this?
September VHF.
630 points.
Which category do you in?
Single operator portable analog only.
Okay. Good deal.
New niche option. I pulled.
You probably won it.
I've set 3 records, including breaking my own once between the 3 contests because it is
Because everyone's NFTA.
a lesser entered category in this region. All right. Any other entries for bragging rights, upgrades, call sign changes, or silent keys? Any Globe DX, perhaps?
Look at you, DX.
I'm off the air for the last 3 weeks.
I know, your tower's now.
All
All
right.
my antennas are down.
I did manage to get Japan during a POTA activation.
Excellent. That does count as a good DX.
Marshall Islands FTA.
Catch that.
What?
Marshall Islands on FTA. Yeah, it's on FTA.
All right, anyone else we want to rustle up on this category? Hearing no additional, move on to VE reports. From online, we have Paulette's VE report from August, where there were 9 candidates with 5 technicians, 3 generals, 1 extra, served by 7 VEs. This is in turn on the VE list.
Yeah, okay.
And for September, we had 7 VEs serving 3 candidates, 2 technicians, and 1 upgrade to extra. And I believe we have in progress on VA liaison work, but if you're interested in being a VE, come talk to us. We can get you over on the VE mailing list. I'll on the groups.io, and you can join in first Saturday of the month. Testing starts at about 8 a.m. In this room now. All right, going through our list of opportunities. Bike the Barns is September 21st. Badger Challenge is also September 21st. Save the date for the Flark Holiday Party, Tuesday, December 2nd. We do not have an official event, but Winter Field Day is January 24th and 25th of 2026. And we will be continuing planning for Field Day, June 27th and 28th, 2026. Are there any other opportunities that people would like to have added to the list?
This Saturday is the Wisconsin Parks on the Air event.
Yes. That's the 20th?
Now, if you're just looking for operating events, the Belvedere Hamfest is the last Sunday of the month.
That was the one that made the rounds on various email lists this weekend. Okay.
What day is the September one?
It's the last Sunday of the month, where the 30th, I want to say, maybe the 29th.
That's the Chicago Athletic Club.
I don't know why they do
It's
it.
the big one from Chicago that used to be in Zion years and years
The
ago.
last Sunday will be the 28th.
It's the 28th. Okay.
It's a pretty big ham fest. We'll get most of the Chicago operators out there.
Any other entries to include in that? All right. Moving on. For old business, we are continuing field day planning. Come talk to us if you want to be added to the field day operations committee list. We have our lead, I believe, here today. So we're trying to close on plans because we can't be guaranteed our typical field day site in 2026 due to Dane County Parks construction. And so we're trying to close out on our alternatives prior to reservations opening in November. Is there any old business I should be aware of that didn't make the agenda? All right, new business. The club acquired a surplus tower.
40 feet of room, 20, the light duty stuff. But a 30 pounds section, it's pretty easy to raise a field day. I can bring anything heavy on it.
So we have
It's
that.
unfortunately not as light as the old one used to have, which was aluminum, but I mean, it's G20, so lightweight, heavy duty, lightweight TV grade. But we got 40 feet of it. So a little less than, we got 30 feet, the bottom section got bent when it was coming down. So we have
What for surplus?
2 sections, a top section and one that's bent at the bottom. So we can put up 30 feet plus mast, which is fine for field day.
We'll see about designing some support equipment around that over the coming year, so we can deploy that effectively in the future. Does anyone have any new business to submit for the meeting tonight?
How about trying to find U-bolts for the beam before next field day?
Well, what we need to do is get a mast that is appropriately sized,
Okay.
that will fit on that.
Still didn't have U-bolts.
Okay. We need a 1 1/4 inch mast, which is what should go into that tower. And that would then fit the antennas.
Okay, put that down as a note. Any other new business? All right. With that, we will move on to the program portion of our meeting tonight. So tonight we have W6DQ presenting amateur radio astronomy. Dennis, go ahead and take it away, please.
Okay, thank you very much. I'm going to go ahead and share the screen here. And you should see, hopefully, a blank screen. And I need to move this off of here. Let's see. 1 second. There we go. Okay, that's good. Yeah, I got multiple monitors here and things don't exactly go the way I expect them to sometimes, but this is good. Okay, so you should be seeing a black screen and I'm going to get started here. You should see the title. Hopefully you're seeing the title screen.
Yes, you're good.
Okay, good. Very good. Okay, we're going to be talking about amateur radio astronomy tonight. And I understand there's some non-ham amateur astronomers there. So want to welcome them and for the interest in learning about radio astronomy, which is really cool. This has been a topic that's interested me a good many years of my life. I'm also an amateur astronomer. We've got a permanent observatory here at our QTH, and the 12-inch Meade LX200. I had to think about that for a second. Okay, so we're going to talk about what radio astronomy is, because it's what exactly do radio astronomers do? We're going to talk a little bit about the history of radio astronomy. I want to talk about that and how we came to understand radio astronomy. I'm going to talk about what I call the big boys, what the real astronomers, the professionals are doing. And then we'll talk about what we can do as amateurs. And there's a lot of stuff we can do as amateurs. And of course, we'll also have a thing where we can find more information. There's a lot of information online on the web to be able to get into radio astronomy. So those of you who do optical and photographic astronomy, optical wavelengths, you're really familiar with things like this. But when we start looking at other spectra, we start seeing all kinds of other things. This is a radio sky image. Here's an infrared image, all sky infrared image. So it looks if you compare those two, they look a lot of similarities, but there's a lot of differences. So the interesting thing is looking at the radio sky, and these images were hand drawn, and I'll talk a little bit more about these a little later. This is really what amounted to the earliest days of radio astronomy right here. So if we look at the electromagnetic spectrum, you can see that if we're doing visible light astronomy, I'm going to get my laser pointer out here. Where the heck are you? There you are. Somewhere. There it is. So visible light. This is if we're visual astronomers, that's where we're looking, is right here in this little tiny chunk of the electromagnetic spectrum. And we are doing photography and what have you here. Now, if we happen to be radio astronomers, we're looking at this entire chunk of spectrum. And of course, I note this is these are the amateur bands right here we're all familiar with from low frequency up into VHF. And of course, we've got microwave spectrum here. But this is where the radio astronomers tend to hang out, is in this area. Okay. And I mentioned, yeah, there's just a tiny slice. So where did this all start? You've probably heard of this gentleman before. His name is Karl Jansky. He was an engineer at Bell Labs, and in 1931, he was researching HF link noise. Back in those days, transatlantic telephone calls and what have you were done on HF, over HF channels, and they were plagued with noise. And so he was trying to determine what the source of this noise was and if they could somehow deal with that. Well, he did find. He ended up with he built this large steerable directional array, and I'll show a picture of that in a moment. But he found three sources of noise. One was nearby thunderstorms, lightning. Of course, we're all familiar with that in radio. Nearby thunderstorms, distant thunderstorms, and the one that was puzzling was a pervasive hiss in some particular directions, not related to thunderstorms or anything. It was just a hiss. This is a photograph of his array. And this is at 20.7 megacycles or megahertz. I'd like to have something like that in my backyard. Nice big Sturba antenna array. That's really neat. Well, the HIS had some interest. There was some interest in what was going on there. He realized it wasn't the sun, and it was located at a fixed position in the sky. Oh, well, of course, uh, in not that it's always in the same spot in the sky, but in the astronomical sky, it's in a fixed location. Okay, and his conclusion was that it was the core of the Milky Way galaxy. And once he made that conclusion, he never pursued it any farther. That was the end of it. So he's now recognized today as the discoverer of radio astronomy, and we honor him with a unit of signal strength that's called the Jansky. So the next big event, and this is actually an amateur radio connection, which is kind of fascinating. Grote Reber in 1937. He's W9GFZ, amateur radio operator, and he built this 9-meter dish in his backyard, so big antenna. And the drawings that you saw earlier, those hand-drawn images, those are his. Those are things that Grote Reber did in 1937. He's mapping the sky at 160 megacycles, or now what we'd say megahertz. It took him a few tries to get it right. He was a lot of interference. He was trying at different frequencies. He started out at much higher frequencies and wasn't having much luck. So 160 megahertz or 160 megacycles is where he really found some interesting things. But his operating hours were limited. I've read stories where he was getting interference from taxi cab radios. So that was one of the things that he had to deal with. But interference caused a lot of problems for him. But he did publish. He published something called cosmic static. Okay, what's going on here? There we go. It was published in the 1944 edition of the Astrophysical Journal. And in reality, this marks the beginning of what we call intentional radio astronomy. This is where the game really started. And I've got some pictures of his antennas, or antenna. The one on the right is a photograph of it originally in his backyard. The one on the left is at the National Radio Astronomical Observatory, where they relocated the antenna some years back and put it on display there. It's now a monument to Grote, and that's him. That is Grote Reber standing in the front of the antenna there. So this is at the National Radio Astronomy Observatory. So what did his results? Well, you saw the results. This is what his recordings. He recorded the signal strength. And as he moved the antenna around the sky, he could record the signal strength. And when he analyzed those signal strengths, he was able to come up with a map that show kind of like isobars in a weather map, or in a topographic map, the lines on a topographic map. So he was able to graph the signal levels in the sky. And so these are at two different frequencies. The top one is 160 megahertz, and the bottom one is 480 megahertz. And this is done in his home in Illinois. So he mapped the Milky Way galaxy, and this is the first attempt at that. So he's dismissed by these astronomers of the day. You know, astronomy was optical. We had these big optical telescopes, and they scoffed at him. They said, "This is not real. This is not real science." And it wasn't really considered to be important research, but he persevered, thankfully. He remained an amateur astronomer until his death. And interestingly enough, he was doing research at VLF frequency, very low frequencies, long wavelengths, and doing research with NASA and the shuttle program, interestingly enough. And he moved to Tasmania, and he felt Tasmania had good transparency in the ionosphere to be able to do his astronomy working with NASA. And some of the later diagrams that he did are right here. This is at 144 meters wavelength, or roughly 2 megacycles, 2,000 kilocycles. So he really did start something. He was able to predict one of the things that came out of this was the prediction of radio spectral signs. Now, radio spectral lines allow us to identify different elements and molecules in the universe. Very important aspect of astronomy. Now, we've done that, optically with spectrography with an optical telescope looking at different wavelengths. Well, The idea is to do this with radio astronomy to identify many other elements and molecules. Well, in 1944, a fellow by the name of Jan Oort, and you might recognize that name, he describes this. He describes that we should be able to identify spectral lines in radio transmissions or radio emissions. One of his students, Hendrik van de Hulst, was tasked with the problem of identifying hydrogen, which is, of course, the most abundant element in the universe. Because it's so abundant, it should be real easy to detect. And they predicted that the frequency at which we should be able to spot the hydrogen line is at 1420 megacycles. The reality was it proved real hard to detect. And that transition, as we say, the transition from ground state, which is what we are actually receiving, is the transition of ground state of atomic hydrogen, is rare. And the number that comes up is 2.9 times 10 to the minus 15 times per second. Well, that's pretty thin, pretty thin odds of finding something. Well, by 1951, a couple of gentlemen at Harvard University, Evan and Purcell, they succeeded, and I love their telescope. I think it's pretty amazing setup, and it reminds me of some of the things that I've played with over the years. But what that number works out to is about one hydrogen atom per cubic centimeter, one hydrogen atom per cubic centimeter in the universe. But there's a lot of cubic centimeters in the universe, so it should be easy to find. There's the Harvard telescope, and you see, I see some familiar things. This actually looks like a National NC-183 receiver that's been modified. There's some waveguides floating around here and some other test equipment, a chart recorder. And this is the equipment they use to find the hydrogen line. This antenna, this big horn, is in a fixed position. And it's used in what is called a drift scan mode, where the telescope is fixed at a fixed position relative to the Earth and uses the Earth's rotation to sweep an image of the sky. And so you can change the elevation of this horn and map the entire sky by doing that. So these are the guys that actually discovered the hydrogen line. They actually found it, and it's a real significant discovery. This is the hydrogen line at 1420. One of the things that they discovered when looking at the hydrogen line at 1420 is that they were able to detect a Doppler shift on it, just like we do in optical astronomy. We get red shift and blue shift in optical spectrography. They detected that Doppler shift. And with their measurement, they were actually able to measure the angular velocity directly of the Milky Way galaxy. That had never been done before. And one of the things that it revealed was that the galaxy has a spiral structure. This event of discovering this hydrogen line is the basis of all modern radio astronomy. This is where we actually build on this today. And that hydrogen line measurements continue to this day. And we'll talk about how you can do that yourself. You can do your own hydrogen line measurements. And you can actually do it without any cost, which I think is the wonderful way to do it. Today, that frequency, it's actually 1420.40575 megahertz. It's protected by that frequency, that range there, that piece of spectrum is protected by the ITU, and it's called the microwave window. So that's an interesting thing to note there. We provide views of the local galaxy as well as distant galaxies and other far-reaching parts of the universe, and it does lead to what we call a modern conundrum, and I will talk about that a little bit later on. You'll hear a little bit more about this. Radio astronomy and optical astronomy actually came up with a conundrum that we're sitting here scratching our heads about today. So I mentioned about elements and compounds in radio spectra. So each element and compound has a unique wavelength. Just like in optical astronomy and radio astronomy, we have spectral lines. And we can detect those spectral lines. And I just mentioned hydrogen, of course, is 1420.40575. The hydroxyl molecule, our OH as we know it, is 1660 megahertz. And carbon monoxide, these are some of the common things that we can identify, is at 115 gigahertz. So it's at a much, much higher frequency. And we detect lots of elements and compounds. And this is, I haven't updated this. I haven't checked to see this is updated. This is not recent information. This is a couple of years old, so I'm sure this has changed. But radio astronomy has identified 70 molecules in the universe, so 70 that are easily detected, and of some 225 are complex organic compounds. So this is the stuff that radio astronomy is doing. So this is some interesting aspects of it. Now I talk about radio astronomy going mainstream, and here's another name, another radio amateur, John Krause. You probably have heard of John Krause, W8JK. He wrote the definitive book on antennas. If you've ever seen Krause antennas, that's a wonderful work that he did back in the 40s, and has been published by I think it was published by the Radiation Lab, Rad Lab. It's one of the Rad Lab series books published by McGraw-Hill. He was at Ohio State University and built a really fascinating telescope called the Big Ear in the late 1950s. What's incredible to me, I mean, this is a lot of money in the 50s, but $250,000 was spent to build this telescope. And at the time, it was the largest radio telescope that had ever been built. It's roughly the size of a football field. It's huge. And this, again, uses what we call the drift field design. It uses the Earth's rotation for right ascension. Declination was changed by tilting a flat reflector. And I've got a schematic diagram of that coming up that you can see what this looks like. And there's a photograph of the Big Ear coming up. You can see in this photograph, here's the reflector, the flat reflector, and this can actually move. They can change the angle of this. This is a segment of a parabola here. And these are the receiving antennas right here. So this actually has, because this is a parabola, this has some gain. And of course, these are horns. So the horns themselves have some gain. So this is a very, very large antenna. And so as you might imagine, the way this works is you pick up radiation from a distant object, a star, galaxy, whatever, nebulae. It reflects off that tilting reflector, and it reflects off this parabolic section and ends up back here at this dual feed. And I'll talk a little bit more about the dual feed in a moment. But here are some other photographs of the telescope. So you can see the reflector. And this is immense. This thing is huge for its time. And you can see that this is the feed section. You'll notice that there's two horns here that are separated by a little bit. And a close-up, I think, is, where are we? Come on. There we are. Okay, get it in the right spot. There it is. This is the feed. Now, what he did, which I find fascinating, is he had two antennas, or two feed horns that were 180 degrees out of phase. And so what that tended to do was eliminate any background noise. So we're talking about things like electrical storms and nearby electrical interference, and that it would eliminate that interference and allow him to focus on the RF energy that's really being picked up by the telescope. So following this, we have another major discovery by Penzias and Wilson at Bell Labs. This is the one that really got things started. What they discovered, that there's a constant microwave noise in all directions. This was back in 1965. If you recall, if some of you old timers remember something called Project Echo, when they did the International Geographic Year, IGGY, and Echo, which was a early attempt at a communication satellite. It was a large balloon, and they built these big antennas. Bell Labs was instrumental in this. They built these huge antennas to work with Echo. Well, in putting all this together, they kept finding this constant microwave noise in all directions. And the thing that struck them is it's invariant within 0.01%. And we found today that it's even more invariant than 0.01%. And this is what we today call the cosmic background radiation. It was Dickey at Princeton that figured out what it was. The guys, Penzias and Wilson, found it, but they didn't know what it was. But Dickey figured it out, that cosmic background radiation. And this is the remnant, what we believe is the remnant of the Big Bang. This is what's left over after the Big Bang. And this is the background noise of the universe. We like to talk about signal intensities in terms of degrees Kelvin noise temperature. So absolute zero, we're 5 degrees above absolute zero. So 5 degrees Kelvin noise temperature, it's absolutely uniform throughout the sky. So this is what led to George Gamow and the Big Bang Theory, was his concept. So this has been one of the longest running data collections from when they worked this in 1965 to present day. This is still taking place. Observatories throughout the world are involved in this, and we're both doing both ground-based and space-based operations. So there's a lot going on with this. And of course, this is all in support. This research supports the concept of the Big Bang Theory that was proposed by George Gamow. So technology, let's talk a little bit about technology. The earliest telescopes, like Grote-Reber's telescope, had a single antenna, and it was a big parabolic dish. Generally speaking, a bigger dish was better. The bigger, the better. If you could make a really big dish, you were going to have a really good antenna. And we know about some big antennas. Jodrell Bank in Great Britain, Green Bank, West Virginia. In fact, Green Bank, West Virginia is the largest movable object on Earth as a machine. It's the largest movable object. It's a pretty impressive telescope. Arecibo, of course, we're very sad about Arecibo because Arecibo collapsed, but Arecibo was a very large radio telescope. It didn't start life as a radio telescope. It was actually began life in doing atmospheric research of all things. And of course, now China has the largest single antenna, which is over a mile in diameter. So it's quite a bit larger than Arecibo. But new technology, we didn't need a single antenna. We could actually start using multiple antennas and do interferometry. So multiple antennas, multiple receivers. We collect the signals and we process them. And we can actually, with 2 small antennas, make one very large antenna. Or if we have a lot of really small antennas, we can make one substantially huge antenna. So we use great geographic separation. So you're all familiar, you've probably heard of the Very Large Array in New Mexico. This is a large interferometer, but there's one that's even bigger than that. That's called the Very Long Baseline Array, the VLBA, that literally spans the globe. So it's a very, very large telescope. Using interferometry, we can synthesize a single huge antenna. But it has some requirements like precision timekeeping. It requires extremely precision time because you're correlating all the data coming from different spots on the surface of the globe. The correlators tend to be rather complicated. The correlator today, we use, I wanted to talk about fast Fourier transform. We don't want to get into that in this talk because we could do an entire talk on Fourier transform and fast Fourier transformer. But this is the tool that's used in radio astronomy today. And it's the idea of analyzing the frequency components of radio signals of electromagnetic radiation from the sky. We receive that in the time domain, and we use the fast Fourier transform to convert that into frequency domain and generate what we call a power spectra of the sky. And so this is the process that we go through, and using multiple apertures, knowing we have this talk about this here. This is the multiple apertures. We got 2, in this case 2. We can have many, many more than 2. In fact, some of these arrays use literally hundreds of antennas, each with its own receiver and tied into a correlator where we do the fast Fourier transforms and generate an output signal, introducing a phase shift. Obviously the phase shift because of the baseline between these 2 antennas and receivers. So this is the basis of interferometry today. Now, I'll talk about some of the National Science Foundation runs a number of telescopes here in the States. NRAO, which I mentioned earlier, the National Radio Astronomical Observatory. And of course, they have the VLA, which we mentioned in Socorro, New Mexico, and the VLBA, the Very Long Baseline Array, which I mentioned spans the globe. So we have antennas that go from Hawaii to the Virgin Islands. And there's, I think, I want to say there's 10 antennas in that array. Also, the Green Bank, West Virginia, we have the Green Bank telescope, the Robert C. Byrd Green Bank telescope, which is the largest steerable dish. This thing is immense. It operates up to 300 gigahertz. Now we're talking about little tiny wavelength. I mean, this is sub-millimeter waves. And then, of course, we have the National Astronomical and Ionospheric Center, and that NAIC was who operated Arecibo, and they've operated some other facilities. But I have to scratch. Unfortunately, I have to scratch Arecibo. I would hope someday that that would be rebuilt. We don't know. We can be hopeful, but we don't know. So I mentioned the Very Large Array. Some of you may have visited the Very Large Array. That's the VLBA in Socorro. But the VLBA, this Very Large Baseline Array, there are 10 sites, Hawaii to Virgin Islands. We have Washington to New Hampshire here in the continental United States. They operate in non-contiguous bands, and typically they're 300 megahertz to 90 gigahertz. So they're still getting up into sub-millimeter wavelengths. It's operated out of Socorro, New Mexico, where the VLA is operated out of Socorro. And the resolving power, and this is the thing, this is what you gain with something like a long baseline array. The resolving power. How would you like to be able to read a newspaper in Los Angeles from New York City? That's what that system, that very long baseline array, that's the resolution of that antenna. This is one of the antennas that's located here, not far from where I live here. It's just an hour's drive north of us, a little over an hour's drive north of us in Owens Valley. That is their antenna. This in the background, this is actually Caltech's Owens Valley Radio Observatory back here in the background. And they have a number of antennas here, again, doing everything up into the sub-millimeter wavelengths. I mentioned the Richard C. Byrd GBT. This is that antenna, which is quite large. It's that is a 100-meter diameter dish. And one of the really interesting things about this, if you notice, if you've got like DirecTV or Dish Network, you'll notice that they're a little odd the way their antennas are set up. It's called an offset fed dish. So the feed, which is located up here, this is the feed, is not in the signal path coming in from the sky. So you don't have a shadow on the dish. There's no shadow of the feed. If you look at traditional antennas, let's take a look at this is Arecibo. You have a structure that holds at the focus with the receiving hardware here. And this forms a shadow in the image and does tend to distort things and causes a problem. So the GBT doesn't suffer from that issue. And of course, we all know, and I this is tragic. I had to say Arecibo resulted in an unfortunate accident and is no more. There was a lot of research done with that, a lot of amazing research done with that antenna and that telescope. So we'll start looking at some other things. This is the Canadian Galactic Plane Survey that's done in radio frequencies. And it's a composite image of Cygnus, the Cygnus region of our sky. The reddish colors are actually a 74 centimeter emissions. The 21 centimeter green emissions are hydrogen gas. We have infrared that was collected by IRIS, which was IRIS was an on-orbit telescope, and the turquoise colors are 60 micron wavelengths, and the blue are 25 micron wavelengths. So this is a composite of a number of different images, but you can see some amazing things in here. These are nebulae here, like a remnant of a supernova, Many of these are supernova remnants, and of course, all of this gaseous region are all supernova remnants. This is in Cygnus. Now, Cygnus is a very, very bright radio source. So this is an easy target for amateur astronomers, radio astronomers. One of the interesting things is trying to image stars. So this is a Hubble image of Betelgeuse in visible light. And when we take and look at this at radio wavelengths, we see something a lot different. And so this is the disk that you see optically, but we see a lot more going on here in the Betelgeuse at radio frequencies. And I want to say I can't remember what frequency this is at. I don't think it says on here. Oh, at 43, yeah, it's right there, the title. Duh, it's right in front of me. 43 gigahertz. This is their image of Betelgeuse. So quite interesting. A.J. Beasley, we had a relationship with Tony Beasley. He was the director of the Owens Valley Radio Observatory just up the road here. And we got to spend a couple of years with them doing moonbounce. And I have another program that I've done on doing EME using a 40-meter dish that we call EME on 40 meters. And that was thanks to Tony Beasley right here, who was part of this image from NRAO. So other things that VLA have discovered, how about discovering ice on Mercury? Because it gives off a particular wavelength. They were able to receive that and find out that there's ice on Mercury, which is really kind of hard to believe. So we're going to shift a little bit. Let's talk about, we're going to talk about amateurs now. They got some cool, the big boys have got cool toys. We like that. But amateurs have got some really, a lot of capabilities, believe it or not. And there's a lot of areas where amateurs work. One of which is VLF, which is probably the easiest to do, is solar observation. And I'll talk a little bit about that, how we do that. We can do HF planetary observation. There's a number of sources within the solar system that give off HF radiation that we can detect. And of course, we look at microwave doing radiometry, which is measuring the signal strength, radiometry, the heat of the radiation, and of course hydrogen line. That's obviously available to amateurs, and there's many opportunities for amateurs. We have opportunities with costs that range from free online radio telescopes to you could spend tens of thousands of dollars and build your own in your backyard. One of the things I like to say, if you've got an old DirecTV or Dish Network antenna, you can build a real simple radiometer and look at the sun and other objects in the sky. So let's talk about VLF solar observation. One of the things we know, as amateurs, is how solar radiation affects HF propagation, but more importantly, it disrupts VLF propagation. And what it does, if we have coronal mass ejections, for instance, will cause a disruption to VLF. Well, there's some great VLF sources that we can listen to, like WWVB, which is down at 60 kilohertz. We used to be able to listen to the, what do I want to call it? Why can't I think? Other VLF sources down on 100 kilohertz, but getting down into the spectrum below 100 kilohertz, this is very susceptible to disruption by coronal mass ejections, and they're very easy to detect using real simple electronics. So that we disrupt that. The simple instrument, it's about as simple as it gets. You can pick one of these things up off of eBay for practically nothing as a WWVB receiver and comparator. And you just need a stable reference frequency to go with that. And you can start looking at these CME disruptions to VLF. So that's solar astronomy is we're looking at. The WWVB receivers, I've got one sitting here somewhere on the floor next to me. It's an old HP instrument from the early 60s. And like I say, you can pick these things up for practically nothing at the swap meet, on eBay, and it makes a great solar receiver. So we've got new ground with VLF. One of the new things that we're looking at are gamma ray bursters on VLF. There's a correlation between gamma ray bursters in the optical submillimeter and the HF and VLF spectrum and X-ray spectrum, so that they're looking at these gamma ray bursters all over the place. And as amateurs, we can actually look at that as well and record the data. Amateurs have found heretofore unknown meteor storms that disrupt low frequencies. So there's another opportunity. The real opportunity today is what we call sudden ionospheric disturbances. And you may have heard of this term in correlation to earthquakes. There's a lot of research being done on SIDS with earthquakes. And we do know where we live here, if you recall, in 2019, our valley here where we live suffered a 7.1 magnitude earthquake, plus a series of aftershocks, and a 6.4 magnitude foreshock. So we had some massive earthquakes here. Hams here in the valley noted that on HF, propagation was affected by those earthquakes. And it's all part of this sudden ionospheric disturbances. We noted that HF propagation changed before and after the earthquakes. So that was a direct correlation, which to me was kind of fascinating and something that a lot of research is being done with, because we're looking at that as a means to predict earthquakes, which heretofore we've not been able to do. That's a big one. So this is typical of what you might find. Here's a typical HP 117A VLF comparator. Typically, you can pick these things up nowadays, even less than $100. This was a few years ago. This is the receiver, and there's a chart recorder, and the chart measures the phase difference between a local oscillator, a stable, in this case, it's a crystal oscillator, and the ground wave we're receiving from WWVB. And what happens is that ground wave, the comparator shows you the change between ground wave and sky wave from daytime to nighttime. And what happens is if we get a coronal mass ejection, it gets totally disrupted. And I think I've got a picture in here of what it actually looks like. You'll see. So this is another type of instrument. This is a Spectracom 8164 that I have. These things were a little bit more expensive. I like the HPs are really much nicer. But if you look at what this actually looks like on the chart, this is what we talk about going from skywave to ground wave is called the diurnal motion. And you can see here, this was a CME that occurred and just totally messed up communications here for a short time, for a number of hours. So this is what we look for, that CME on WWVB. Okay, let's move on to HF. I'll talk about HF a little bit. NASA, along with the University of Maryland, I believe it is, if I'm not mistaken, has something they call Radio Jove. This is an ongoing project, and primarily it's interested in getting young people involved. That's like a STEM program that they've done. And the idea of Radio Jove, Jovian planets, we want to look at volcanism on Jupiter's moon Io. And Jupiter's moon Io is rich with sulfur volcanism and has been detected by the Voyager probes and others. And this actually shows up in the 18 megahertz range for sulfur. So we can actually listen to that and hear it on an HF receiver tuned to 18 megahertz. And this is what the purpose of Radio Jove is. The other side of this is we know there's huge electrical storms on Jupiter, and there's lots of emissions, electromagnetic emissions from those storms at 20 megahertz. So this is something else we can listen with nothing more than a short wave receiver and a decent antenna, and to be in a quiet location. Small, not much noise. 20 megahertz, we can build a pretty nice Yagi antenna and point it at Jupiter, a small Yagi. The other thing to do is watch this website, spaceweather.com. If you're not already watching that spaceweather.com, I'd suggest you do. There's some really great information on there that refers to propagation and what have you, but they actually predict these the sulfur volcanoes emitting and the EM emissions from Jupiter on 20 megahertz. So they're predictable. And so you know when to look for them. Let's see, spaceweather.com, and we can get more elaborate. We can actually do HF interferometry, and there's a lot of this going on. I don't know of any amateurs that are really doing that. That's something that I would like to do. It interests me, but it requires multiple antennas, multiple receivers, and a way to correlate the data. And the receivers and antennas are fairly easy to do. I can tell you that up at Owens Valley, the Owens Valley Radio Observatory, they have something that's called let me think about it for a second. I can't remember the name of it. Oh, shoot. It's an HF array that has something like 128 antennas, and they're broadband antennas that cover the HS spectrum all the way up to about 100 megahertz. And they're doing a lot of research at those frequencies. So the means to correlate data, that's computers with FFTs, for fast Fourier transport. So I'm going to talk a little bit more about Radio Jove. I'm watching our time. I have to share, I have a hard stop a little bit before 9 o'clock your time because I'm what I call the net control operator for a big net here that starts at 7 p.m. that I can't miss. So I have to be there for that. So I've got some more slides here. We'll keep going and hopefully we'll get through all of this and have some time for some Q&A. I'm sorry, I said University of Maryland. It's University of Florida. I misspoke, but it's NASA and University of Florida. And it's to get school kids interested in science through radio astronomy. The idea was to provide inexpensive resources to them, provide lots of background information, lots of material. It's all freely available online. And the hardware for this is available as a kit. It's a receiver, it consists of a receiver and an antenna system and free software, which is this thing called Radio SkyPipe that you could download from their site. And from this, we can do things like observe the volcanism on Io, and we can observe the electromagnetic storms on Jupiter. It's fascinating stuff. I've got an example of some work that was done by amateurs, by students. This is the Starlight Cascade Observatory, the Radio Jove project. What you see here is this is the receiver kit. And this antenna is basically just two dipoles. It's two phased dipoles at 20 megahertz. There's one dipole here. Let's see, you're probably not seeing that. Oh shoot, I don't have the slide up yet. Stand by. Hang on. There we go. I'm sorry. I blew that. There's the circuit board. I'm looking at the wrong screen. And here's the antennas. There's two dipoles. There's one dipole. And there's the second dipole that are set up as a phased array. And some of the things that they've looked at, this is what's interesting, is how about not just looking at Jupiter and its moons, how about looking at the sun? How about an X-class solar flare and how it disrupts communications at 20 megahertz? And this is one of their recordings using Radio SkyPipe. This is what the results look like from their system. So this is the kind of thing you can do. And this is a fairly inexpensive kit that's available. I think it's still available online. And if you happen to be a science teacher and involved in STEM programs, what an amazing thing to be able to do. This is really great stuff. So microwave radio astronomy, I'll move on to that. We can do radiometry. That's the easiest thing to do. And the big target for radiometry is the sun. We measure the total power within a given bandwidth. So in other words, the total power we receive from the sun within a given bandwidth. This becomes exceedingly simple to do. Like I mentioned, a DirecTV dish and low noise, using the low noise, what they call an LNB. It's a low noise block down converter. And essentially, all you need is a DirecTV dish with the LNB and one of the little tools that they use to align a satellite dish with its target satellite. And there's just a little meter with a detector, and that's all that's needed to do this, basically. You need a power source for the low noise block down converter and a means to detect and collect. And the means to detect and collect is it's basically a meter with a detector. We use a drift field technique. And here's an example of what a fellow built. This is from Peter Wong, the itty bitty radio telescope. You see, we just have a small dish. There's the LNB. Sorry about that. Uh, Next picture. Oops, thank you. I'm looking at the wrong screen. I keep looking at the wrong screen. I apologize. This is their itty bitty radio telescope. You see the satellite dish. Here's the LNB, and he's got this little meter right here. In this case, it's called a sat finder. These are used by installers to align the satellite dishes, and they're very, very inexpensive. And there's a power source, like a 9-volt battery, to run this thing. And this will produce, again, kind of like what Grote Raber did. You're looking at the total power from the sun on this meter, and you can kind of graph things out and see what's going on in the sky. So this is a simple thing to do, probably with stuff that's just lying around, possibly, that you have. Certainly it's stuff that I have lying around here that I can put one of these together. But if we get it more serious and get it a hydrogen line, we want to look at that 1400 to 1600 megahertz spectrum. What's really cool is we have something that's on the internet called Pictor. Pictor is an online web-based hydrogen line telescope. That's the easiest way to start doing this. Now you can build your own, and he gives the complete breakdown of how he built this telescope. So you can actually do this yourself. The hardware to do so is readily available. A lot of it can be had on eBay, all this hardware, but build your own. It doesn't require a lot of elaborate equipment. We talk about, if you've ever heard the term TVRO, the old days of C-band satellite antennas, what we call buds, big ugly dishes, a TVRO dish. You can actually probably get one of those for free, or you may have one in your backyard that you don't use anymore. You may have a neighbor that has one that would love to get rid of it because it's an eyesore in his backyard. Get it for free, and you've got the start of building a telescope. You need a low noise preamp and a down converter that is, of course, at this our target frequency range here at 1400 to 1600. You need some kind of SDR. You need like a computer running Windows and the software for that. Easiest. We use the stuff we use is RS-based Cloud SDR. That's the software. Another one we can use is SpectraView, is another piece of software. That these are all available online for free. Or if money's no object, you can buy one. You can have a telescope built for you. You don't need to build anything. You can actually, there are companies out there that will build radio telescopes. So that's one way to get through this. And if you really, really get serious, build your own telescope. So as an amateur, what are we going to look at? What kind of stuff are we going to see? Well, of course, the Milky Way galaxy. We've talked a lot about that. We can look at Cassiopeia A. That is pretty much the brightest radio source next to the sun in the sky. It is a supernova remnant. Cygnus A is another great target. It's the second most energetic radio source that we know of. It's a radio galaxy located in the constellation Cygnus. This has been observed from low microwaves all the way up into X-rays. We also have Taurus A is another big one. That's the Crab Nebula. If you're familiar with that one. That's another supernova remnant. It's very noisy in the hydrogen line. And Virgo A is yet another. And of course, we'll talk about looking hydrogen line on looking at Sol, our sun. So what does this take? Proof. What do we get from this? And this is the thing that I talked about this conundrum. This is going to pop up here momentarily. What we can do with microwave radio astronomy is we can prove that the Milky Way is a spiral galaxy. We can't really do that optically. But if we use something like Pictor, we can actually collect data from Pictor and do analysis on it and create a model of the Milky Way that shows us where the spiral arms are. So we know that it's a spiral galaxy. And I'll show you how that works in a minute. But we use drift field, such as Pictor, which is a drift field telescope. We get, what we'll see is in one spectrum display, we'll see multiple instances of the hydrogen line that are Doppler shifted because they're farther away. And because they're farther away, they're moving at a different angular velocity, which causes them to be Doppler shifted. What this led to, and I'll talk about why it leads to this, you can demonstrate the existence of dark matter, what we call dark matter. If you calculate the radial velocity of the Milky Way and you measure what you do is you calculate the radial velocity of the Milky Way, another rate at which it's spinning. You calculate that based on what we know is the estimated mass of the Milky Way. And we measure the radial velocity with a radio telescope. Those numbers do not agree, and they do not agree by quite a large amount. So this is the conundrum that I talked about earlier. This additional mass is unaccounted for. It can only be caused, well, that's one thought, is it's caused by additional mass, which we can't see, we can't detect, so it's called dark matter. That's where the name comes from. So it's an interesting thing. And it's something that we can actually look at with amateurs and actually prove this to ourselves. So here's a rather complex diagram that shows the picture results from Cygnus A. And what this is if you basically you schedule an observation period on the telescope collects the data, puts it in an email, and sends it to you, and this is the result that you get. So the thing that's really most interesting in here is this is the average spectrum. This is the one that we really want to look at, this calibrated and normalized spectrum right here. And what we see right here, this spike, this is hydrogen line. And I mentioned that we have additional Doppler shifted hydrogen lines, and you can see those in this image here. There's one there, and there's one there. And if I zero in on it, look at that. We blow it up a little bit. This shows this is three hydrogen lines here, which corresponds to three different arms, spiral arms of the galaxy that are shifted to different wavelengths. So this is something that you can actually show yourself and demonstrate this. Those three distinct bumps, blue shifted to a higher frequency means a higher radial velocity, and it corresponds to three arms of the galaxy. Each is blue shifted farther because it's got a higher radial velocity. Think about points on a disk is the way that we like to think about this. And what we do is through drift field, we can look in different directions. And over time, we can build up an image of many, many recordings like this one that I show here from other directions that we can build up almost a 3D model of the galaxy. So we use different elevations of the antenna. We have multiple azimuth swaths of the sky. And what we end up with is we aggregate all of those measurements and we can produce an image that looks like this. And this being the direction of observations, for instance, here, like we're just looking at Cygnus, if you look at this line right here from Cygnus, this is us right here in the Milky Way. We're located right here.
Advance the slide.
Oh, I'm sorry. Doggone it. I did it again. Thank you for that. Thank you for reminding me. I'm looking at the wrong slide in front of me. Okay, let's try that again. Okay, so this is us right here. That's our solar system. That's where we're located. This is that line of sight to Cygnus that we show those observations. And if you plot out all the lines, basically all these different directions, getting the results, if we plot those results, these are the things that show up, are these lines here, which are those peak hydrogen lines. And these, of course, correspond to the spiral arms of our galaxy. Now, some parts of the galaxy we can't see. They're in shadow, and they're in shadow because of the galactic center. There's just too much obscuration of the view there to be able to see these things. But other than that, we can actually show these outer spiral arms and the different spiral arms of the Milky Way, which to me, as an amateur, to be able to do that is fascinating, to be able to do that sort of thing. And so how do we rationalize the dark matter? This is the problem. Now these are data points from M33. And so this is a radio galaxy distant, and we look at things like these are the observations from starlight and what we would estimate to be the actual observations that we make. This dashed line is what we expect it to be. And this is from our observations as the visible disk of that galaxy. This is what we'd expect to see, and this is what we see instead. And the difference between these two is the problem. This is the conundrum that leads us to think about dark matter. We don't know what causes this. This is what we should expect it to see. Maybe there's something wrong in the way that we're estimating the mass of the galaxy. Possibly that's what it is, but a better explanation is this idea there's a dark matter, something there that we can't observe because it's not emitting anything. There's no radiation being emitted. So that's the whole thing about dark matter. We're down to a couple of more slides here. Let's see. So the expected velocities differ, like I just mentioned, and what does that mean? That one theory is dark matter. A halo of dark matter around the galaxy would explain this. That's one explanation for it. It's yet to be proven. We don't know. It's just one of those big questions in astronomy today, and we can show this. We can show this ourselves with the Milky Way using the techniques I talked about, observing hydrogen lines, and plot the observed velocity against what should be expected for the Milky Way. That's not the expected result. So what next? I invite people to and encourage them to go visit radio observatories. If you get a chance to get to Socorro, you can visit the VLA. There's a big visitor center there. You can go to the VLA. You can go to places like the Green Bank Observatory, the National Radio Astronomy Observatory. You can visit Owens Valley Radio Telescope here, and Radio Observatory here welcomes visitors in our part of the country, and you can visit part of the VLBA there and see that. So this is the kind of thing that we want to see next. Visits to local observatories, and like I say, you're kind of not close to us here, unfortunately. You're on the halfway across the country, but they do host visitors, as I just mentioned. OVRO does. This is owned and operated by the California Institute of Technology, Caltech, and it's located about a little over 100 miles north of where we are here, where we live here in Inyokern. And of course, we've got the VLA in Socorro. That's operated by the NRAO, and you can find more information about that at their website. By the way, I am going to send Nicholas. I will send you a PDF of all the information in here, all the websites and all of that. So nobody needs to worry about copying that down. I'll forward that to you. And if you'd like a copy of the slides, I'm happy to share those as well. I will do that. But VLA at Socorro, Green Bank, West Virginia, and of course, Pictor. You can Google that if nothing else, but pictortelescope.com and find it. It's actually located in Italy. Radio Jove, you can get that from NASA. Again, I say, Google Radio Jove, and you'll find all kinds of information about it. That's their website. The other thing you'll find fascinating, we have lots of astronomy clubs around the country. Do you know that there's a amateur radio astronomy club called SARA? That's the Society of Amateur Radio Astronomers, and they're headquartered out of the Green Bank Telescope, the Green Bank Observatory, the NRAO facility there. And of course, you can find lots of information about SARA online. And I do believe that is my last slide. It is indeed. And how much time have I got left here? I've got about 10 minutes left. I'm going to stop sharing here, and we'll get back to where we go back here and put folks up here. And of course, I'll open this for questions. I only have, like I say, about 10 minutes, but I'm happy to field any questions. If I can't answer them,
Dennis, first of all, thank you. That was excellent presentation.
You bet. Thank you. I appreciate that. I'm glad you enjoyed it.
Couple questions. So one, have you visited Goldstone, Apple Valley?
Yes, I have indeed. In fact, a personal friend of mine, another ham, was the director of Goldstone and arranged a tour out there. He also, when he left Goldstone, he was the vice director of Jet Propulsion Laboratory. which of course owns and operates Goldstone. So yes, I have been there, and it's a fascinating place.
Yeah, I just wanted to mention because it's, you know, you mentioned a couple opportunities for citizen science. Goldstone actually also has opportunities for people to do citizen science with their 34-meter antenna. You know, if you
Yes,
can
they
get,
do.
my understanding is if you can get a group of people who are interested in radio astronomy, you can reach out to them. They'll actually do a training for you and where you can learn to use the telescope and submit scientific observations. I actually
Yes.
did that weeks ago with Rose City astronomers in Portland, Oregon.
Oh, yeah.
They set it together, so you know, you guys are interested. I think they don't do one-offs, so you got to get like at least probably, you know, at least maybe 7 people together who
Yeah, you need to get grouped together. Now, Goldstone, one of their antennas out there, they weren't using. They basically had mothballed it, and they had essentially donated the use of it to the school district or school system in San Bernardino County, and they never took advantage of it, which is really sad. We were hoping that something would come of that, but that may be one of the systems that they're now using for that, and making it available. But boy, that is a wonderful place to visit. If you can arrange a tour of Goldstone, it's well worth doing that. Now, of course, they're not doing radio astronomy. Their primary mission is the Deep Space Network, where they're observing the deep space probes that are going out to the various planets, like Voyager 1, Voyager 2, all of those things. That's what Goldstone is used for. So anyway, let's see. Oh yeah, somebody posted that. Yeah, everybody can save that. Yeah, rfspace.com. Yes, Spectra View. That's where you get that. Thank you for posting those. I will send that information to you as a PDF, probably in the morning. I won't be able to do it this evening, but I will do that in the morning. You'll get that. So yeah, I'm happy to.
This is Doug, W5WTX. You mentioned the early pioneers. I think Reber was his name.
Yes, Broker. Or Raber. Yeah.
HF and UHF back in the late 30s, early 40s. What were they using for receiver technology?
Oh, yeah. That's a good question. To be honest, I'm not really sure. At 100 in the 30s, I mean, there were some, I've actually got some hardware that's what we call VHF. In those days, they referred to it as SHF, and the VHF, what we call VHF. Some receiver hardware that could have been used in the 30s, that was produced by National Company, that we know of, like the HROs and that type of thing. They made some what they called SHF receivers that he could have used. The thing becomes, how do low noise amplifiers. We didn't know about things like those back in the day, so he probably did a lot of experimenting and probably had to build his own equipment, I would bet. He probably wasn't anything that was commercially available. So today we can buy all this hardware commercially, that we can buy the low noise amplifiers and the down converters and all of that. Just buy it online. One of the sources is a company called Kuhn. Uh, uh, oh, it's DB. It's Kuhn Electronics out of Germany, and I can't think of his call sign. DB7NT. I think that's it. I've got a bunch of his hardware that they sold the company, but that's really the Cadillac hardware from Kuhn for low noise amplifiers and down converters and transverters and things like that. But that's a good source for that. But you can find this stuff on Amazon of all places, believe it or not. Yeah, I'm watching. Where's my time? Where am I? Yeah, I'm coming down to the point where I'm going to have to ring off here, unfortunately.
I'll add something I've seen online, the Discovery Dish project. It's a crowdfunded project for various low microwave receiving. And that gets you satellite weather, and then they also have a hydrogen line special receiver for it. And so mail order capable dish that breaks down relatively easily. I haven't looked into what projects they are, but I've heard of it as a source of dishes.
Is anybody in your club involved in microwave at all? Does anybody do microwave radio like 10 gigahertz? There's a
We have a few people in the area. Thomas over here is attempting
Yes.
to start in 10 gigs, but we have a few people in the area that is not members of the club.
you've got the what is it? The Great Lakes. I can't think of what it's called. It's a microwave group. We've got three microwave groups out here in California. I belong to one called San Bernardino Microwave Society, and there's the Great Lakes region has a microwave society there. There's Texas, North Texas VHF Society. There's another group out on the East Coast. Those are great places to go for great resources for information on all of this. And if you're dealing with microwave, being able to put together the antennas and the receivers, basically the low noise amplifiers and down converters. So that's one to be aware of it. I know I'm watching. My wife is giving me a time hack here because I'm going to have to go in it. I'm really going to have to get going here very shortly. I've got all my equipment warmed up here, ready to go, but I'm the net control tonight. It's at 7 p.m. our time here, so.
All right, well, thank you very much, Dennis. Any
My pleasure.
questions?
Dennis, that was an excellent presentation. Thank you very much.
I appreciate that very much. And if questions come up, feel free to send me an email. It's my call sign at arrl.net, W60Q at arrl.net. And I'm available to answer questions. And like I said, I will send you the material in the morning when I get a chance to do that. Super. Well, thank you for inviting me to your club meeting. This has been a lot of fun. I always enjoy doing this, and it's nice to see a lot of interest, and especially non-ham interest, which is wonderful. Get some amateur astronomers in there. Get them to get their ham licenses too. It all goes together. So with that, if there are no more questions, I will thank you. Thank you very much. I'm going to go ahead and ring off, and hopefully we'll see you again. Maybe do another session like this in the future.
Thank you, Dennis.
Thanks, Dennis.
Thank you, Dennis.
Good night, all 7-3, and hopefully we'll see you again.
All right. Well, at the conclusion of the program, do we have a motion to adjourn the meeting?
Motion to adjourn.
Second.
And a second.
Who's the second?
And 9 T-Rex.
What's your name again?
Rex.
All right.
In TR.
X.
This is a reminder, anyone that's doing motions or secretary like that, please say your name and your call sign. That way everyone online can hear who it is as well.
All right. All in favor, say aye.
Aye.
And those opposed. If you did get a chance to sign in, we do have the in-person sign-in sheet. I believe I picked up everyone I can catch online. We'll keep this rolling a little bit longer. And close out here. Everybody recording.
Yeah.
Both the radio side.